5-3, solving polynomial equations. So in this section, our objective is to solve polynomial equations by factoring and to solve polynomial equations by graphing. Most of the questions that you're going to have to do on your own are going to involve solving polynomial equations by factoring. Our essential understanding is that if x minus a is a factor of a polynomial, then the polynomial has a value of 0 when x is equal to a. If a is a real number, then the graph of the polynomial has a comma 0 as an x-intercept. A is also a root. If you remember back to that chart in 5-2, factors, roots, solutions, intercepts, and zeros all mean the same thing. So if x minus a is a factor, a is a 0, a is a root, and a is an x-intercept. So you can get all that by factoring the polynomial. So that leads us to how to solve polynomial equations by factoring. Just like we used to do with quadratics, we're going to write the equation in the form p of x is equal to 0 for whatever polynomial we are starting with. All that means is set it equal to 0. If it's not equal to 0, make it equal to 0. And then step 2 is to factor the polynomial, factor p of x. Then once it's factored, use the zero product property to find the roots. We're going to start with a couple basic types of factoring problems. Most of them are going to be able to factor out something and then factor it like a quadratic. Or we're going to go through later the other techniques that we could use. So let's start with a pretty basic polynomial equation. So what are the real or imaginary solutions of each polynomial equation? So first, we make sure it's equal to 0. This one is not equal to 0. So that means subtract 3x from both sides, which leaves me with 2x to the third minus 5x squared minus 3x is equal to 0. Then notice that they all have an x in common. So factor out an x. That leaves me with 2x squared minus 5x minus 3 is equal to 0. Now that that x is gone, this remaining polynomial that still needs to be factored is a quadratic. It is x squared. So we are going to use the same techniques that we used in chapter 4 to factor that. And we are going to factor it into two binomials. The first two terms have to multiply together to give me 2x. And the next two terms have to multiply together to give me 3. And that's going to be a plus 1 and a minus 3. And if I FOIL this together, that was the factor method, by the way. If I FOIL this together, we would see I would get 2 whoops, okay, so look, what we have, that would be 2, and that would be negative 3. So obviously that doesn't work. So we want to switch these around and go with that. So now look, we have a negative 6. Now we have a positive 1. Now when we multiply this together, or when we add those two terms together, the two middle terms, we get a negative 5, which is good. Okay. Now, let's set each factor. Each one of these three terms, we set them equal to 0 to get my factors. Set x equal to 0, I get x. Set x minus 3 equal to 0, I get a positive 3. And set 2x minus 1 equal to 0, I get a positive 1/2. So those are going to be my three real solutions to this equation. So x is going to equal 0, x is going to equal 3, and x is going to equal 1/2. And those are my three solutions. Those are also the three places where this cubic trinomial crosses the x-axis. Let's do another. Okay. Again, set it equal to 0. So we have 3x to the fourth minus 6x to the third plus 12x is equal to 0. I should also notice that not only is everything this should be squared. Not only is everything, is there a common factor of x squared, but everything is also divisible by 3. So let's divide everything by 3. If I divide the right-hand side by 3, I still get 0. 0 divided by 3 is still 0. And I can make this problem a lot easier on myself by dividing everything by 3. Anytime you have the chance to do this, you should. That leaves me with x to the 4th minus 2x to the 3rd plus 4. X squared. Factoring out the x squared gives me x squared minus 2x plus 4. Okay. Now I can try to factor this using the same techniques that we just did. For this, I want the factors of 4 that add to 2. Well, the factors of 4 are 1 and 4, they add up to 5. 2 and 2, they add up to 4. So there are no factors of 4 that add up to 2, which means that in order to solve this part of the quadratic, I need to use the quadratic formula, which is plus or minus the square root of b squared minus 4ac over 2a. Okay? Where a is 1, b is negative 2, and c is 4. So plugging those numbers in, we would have 2, negative 2, plus or minus the square root of 4 minus 4 times 1 would give me minus 16 all over 2, which gives me 2 plus or minus 4 minus 16 is the square root of negative 12 over 2. Here's my problem. I cannot leave the square root of negative 12 like that. I need to simplify that expression. And of course, anytime we have a negative square root, we're going to simplify it using I. So the square root of negative 12 turns into I times the square root of 12. The square root of 12, I can make that simpler by saying the square root of 4 times 3. And the square root of 4, I can change that into a 2. So the square root of negative 12 simplifies into 2 square root 3. Bring down the rest of the problem. We have 2 plus or minus that over 2. And then when I simplify this, I can simplify this as 2 fractions. 2 over 2 turns into 1 plus 2i over radical 3 over 2 turns into 1 as well. So we're left with, first, here, x is equal to 0. But it happens twice. So it's equal to 0 with a multiplicity of 2. So it's 0, multiplicity of 2. And so then x is also equal to 1 plus or minus I radical 3. And those are my 4 solutions. 1, 2, because that 0 happens twice. 1 plus I radical 3. 1 minus I radical 3. So let's go through all the different types of factoring techniques that we could use. Factoring out the greatest common factor. Okay? That's what we just did. We just factored out an x. We just factored out an x squared. Anytime, and in this problem right here, we also factored out a 3 to make the problem easier, divided everything by 3. So you factor out the greatest common factors of all the terms. We're pretty good with that. Here's my quadratic factoring techniques that I've used before. Okay? So factoring trinomials. This is both when the number in front is a 1 and when it's a 0. When it's a 1, it becomes a little easier. When it's not, or not a 0, when it's not a 1. So when it's a 1 and when it's not a 1. When it's not a 1, it becomes a little bit harder. So remember, my techniques is to list the factors of 6 and the factors of 10 that subtract to 11 to get my factor form right there. If you're still having trouble with this, go see video 4-4, factoring quadratics. Perfect square trinomials, you hopefully are able to recognize both of those fairly easily and be able to factor them fairly easy. The difference of squares, right? That's when we have no middle term and the 2 squares are subtracted by each other. Now this doesn't have to include perfect squares. For instance here, 4x squared is a perfect square, but 15 is not. We can still factor it using radicals in this case. Factoring by grouping, we had a little bit of practice with that. That's when there's a common factor of these two, and what's left over is the same. So when you see this, it's a little bit harder to see right off the bat, but when you can use this technique to factor a polynomial, you should. The last two that we haven't talked about yet is the difference and the sum and the difference of perfect cubes. These are ways to factor something that is a perfect cube plus a perfect cube minus a perfect cube. We would just have to follow these formats and realize that this term, this factor term, is going to give us one real solution. This factor term is going to give us two imaginary solutions. Okay. Same thing with this one. One real solution, two imaginary solutions. Okay. So let's see a couple new types of problems where we can find real and imaginary solutions using the various factoring techniques. With every problem, the first thing you should do is set it equal to 0. Now, we haven't really had a problem yet with x to the 4th power. The difference with this problem is that we have x to the 4th power, we have no x to the 3rd power, we have x squared, we have no x term, and then we have a constant term. So what's happening is it's going down, right? We're skipping terms, right? This term, x to the 4th, is whatever this is squared. X squared squared would be x to the 4th. So when you have a situation like this, you can think of it in terms of a quadratic. I can factor this. Instead of x to the 4th, let's write x squared minus 3x minus 4. I could factor that fairly easily. It factors into x minus 4x plus 1. I can use those same exact techniques with this problem that's x to the 4th. But instead of my first terms multiplying together to give me x squared like they do here, I want my first terms to multiply together to give me x to the 4th, which means that I'm going to start with x squared. And I'm going to have x squared minus 4, x squared plus 1. Now, unfortunately, over here, where we started with a quadratic, we're now done. On the left, we're not done yet because we can still factor each piece a little bit more. So x squared minus 4, I can factor that like a quadratic, and it is the difference of perfect squares. X plus 2, x minus 2. Now, x plus 1, if we remember back to the last section of chapter 4, that is the sum of perfect squares. When we have the sum of perfect squares, that factors not with real numbers, it factors with imaginary numbers. Equals 0, which makes my 4 answers negative 2, 2, negative I, and positive I. So my 4 solutions to this particular problem, my real solutions and my imaginary solutions, are plus or minus 2, plus or minus I. And if you didn't see how to factor this with imaginary numbers, there's another way to do it. We could have x squared plus 1. We could have just set that factor equal to 0. Subtract 1 from both sides. Take the square root of both sides. Would give me plus or minus the square root of negative 1, which is, of course, I, to get my 2 imaginary solutions. Okay. Let's try 1. That's the difference, or that is the sum or difference of a perfect cube. And in this case, when we subtract 1 from both sides to set it equal to 0, like we do for everything, we of course have the difference of perfect cubes. Following my formula to factor this, we would have x minus 1. Formula I'm talking about is right here. Okay, so we're going to start with a minus and then two pluses. So that's going to be x minus 1 times x squared plus x plus 1. And there's no trick to that. You just have to remember the two formulas for the sum and the difference of perfect cubes. So now, setting the first piece equal to 0 gives me 1. The next piece, I know it doesn't factor, or else this formula would have been factored even further. So in order to solve the second piece, I need to use the quadratic formula, which again, negative b plus or minus the square root b squared minus 4ac all over 2a. Okay, so that gives me negative 1 plus or minus the square root of 1 minus 4 times 1 times 1 gives me a minus 4 over 2a, which gives me a negative 1 plus or minus the square root of negative 3 over 2, which of course the square root of negative 3 is going to be I. So my answer is here, x is going to equal negative 1 plus or minus I radical 3 over 2. And an interesting thing that happens with perfect cubes is you're always going to get one real answer. We're always going to get two imaginary answers, and they're usually going to be able to simplify with some sort of radical 3. Okay, so keep an eye on that, and if you don't get something with a radical 3, make sure it is fully simplified. While factoring is an effective way to solve polynomial equations, we can also find real roots quickly by using a graphing calculator. Not that you will always have a graphing calculator handy for quizzes and tests, but for your homework, it's definitely a good habit to get into, to hop on your graphing calculator or to plug it into Desmos to find the solutions. Okay. So here I have a polynomial equation. I have two choices with this now. I could graph this, and I can graph this, and I could plot them both and see where they intersect. Now, just looking at this graph, it would seem that there's only two places they intersect, but as I zoomed out, I saw that the blue line was getting closer and closer to the yellow line again, and that it probably might intersect somewhere else. Okay? And in fact, because this is x to the third, it does. But that was kind of hard to tell. So a better way, a better formula to plug in would be to set this minus 4x squared plus x plus 5, set it equal to 0. And now when I do this, now I know that whatever polynomial I get is going to cross the x-axis 3 times if it has 3 solutions. And when I graph that, I can see clearly, much more clearly, that it does. And these would be my 3 solutions. So, like I said, most of the time in class or on a quiz or on a test, we're going to be dealing with problems that can actually factor. But let's look at one that you actually do have to graph. So, close friends, Stacy, Una, and Amir were all born on July 4th. Stacy is 1 year younger than Una. Una is 2 years younger than Amir. On July 4th, 2010, the product of their ages was 2,300 more than the sum of their ages. Okay, so we need an x. Well, Una is the only one that's common to both of them. So let's say Una's age is x. Stacy's age. Stacy is 1 year younger than her. And Amir is Una is 2 years younger than Amir. So Amir is x plus 2. Okay. So next sentence says the product of their ages is 2,300 more than the sum. So we would take the sum, x plus 1 plus, x minus 1 plus x plus 2 plus 2,300 would equal x times x plus 1, x minus 1 times x plus 2. Got a little squeezed off there, but that's the general idea. Now if we could simplify that, if I could turn it into a polynomial in standard form, then I could graph it and figure out the ages. So 1, 2, 3x. Minus 1 plus 2 is 1 plus 2300. Okay. Multiplying those together, let's multiply the two binomials first. That's x squared plus x minus 2. Multiplying by x gives me x to the third plus x squared minus 2x. And when I add 2x to both sides, or actually, let's do it this way. Let's bring everything to the right-hand side, so that way I can keep x to the third positive. Okay? So we have x to the third plus x squared minus 5x and minus 2301. That's set equal to 0. I can now graph that, and I get that my graph, which was kind of hard to tell much about. It was a really very linear graph, but across, all I really cared about was where across the x-axis and across the x-axis at 13. So she is 13, she's 12, and he is 15. But, of course, most of the questions that we were going to do will be more like the first question, this one right here, where we have to factor out an x and then factor. This question right here, where we have something that looks like a quadratic, and we have to factor that. Or sorry, something that's a quartic, but we can factor like a quadratic. Or something like that, where we have the sum or difference of a perfect cube. So that is 5-3, solving polynomial equations.